The lab activity for this week is an introduction to thinking about vectors intuitively. Um, and the first few questions ask you to think about vectors even in one-dimensional motion. So let's say that we have an object that's, say we have a ball that's rolling down an incline. This is a one-dimensional motion. We know the ball is just going to be rolling down the incline. What can we say about the velocity and acceleration directions, thinking about them as vectors? So we're going to think of these as arrows with a magnitude and a direction. And really, with this intuitive stuff, all we're really going to be thinking about are directions. We're not going to spend a lot of energy trying to think about the magnitudes of these vectors, although I guess when we talk about addition and multiplication by scalars, that will come into it. Okay, so if this ball's rolling down the hill and it's speeding up because of gravity, what do we know about the directions of the velocity and the acceleration? Well, the velocity is the direction that it's moving. So the velocity will be like this. And then what do we know about the direction of the acceleration? Well, if it's speeding up as it goes down the hill, then we know velocity and acceleration have to be in the same direction. And so the acceleration is also that way. If, on the other hand, let's draw a similar picture. And this time the ball was sent moving up the hill, then gravity would be slowing it down. So what do we know about the directions of the velocity and acceleration in that case? Well, the velocity is the direction that it's moving. But this time, since it's slowing down, the acceleration has to be opposite the velocity. So the acceleration is that way. And we don't usually think of one-dimensional motion in terms of vectors, but you can. And so we are in these first 4 or so problems from this lab activity, 4 problems, you're going to be thinking about one-dimensional motion in terms of directions of an arrow representing velocity and an arrow representing acceleration. And then after that in the lab activity, we'll start talking about vector addition and vector multiplication by a scalar. Okay, so let's say that we have a vector like this, and we want to add it to a vector like this. So how do you do that graphically? There's a mathematical way to do it, which is more of what we do in this class. But there's also a graphical way to think about it. And so to do that, okay, so, and I'm going to then put, let me move this a little bit. I'm going to think of that as the first step in a journey from a starting point to, I guess it would be, you can think of it as sort of like a stopping point, an intermediate point. And then from that stopping point, I'm going to put the tail of the other vector. Okay, so I'm going to put it here, okay? And the resultant vector I'm going to do in red then is the vector that goes from the start of the whole journey to the end of the whole journey. Just think of the resultant as a shortcut from the start to the end. And the order that you add these doesn't matter, because notice that I could have started with this one. Okay, so let's say that this time I start here, and this is the stopping point, the intermediate point. And then from there, I do the other one. Okay. And again, if I take a shortcut of the whole path from the start to the end, that vector looks like this. And notice that those two red vectors are exactly the same. So no matter which order you go in, you can, the vector resultant that you get, the sum of those two vectors is going to be exactly the same. And you can see this if you lay one of these two triangles on top of the other one. You just get a parallelogram that, and the resultant vector is just the diagonal across that parallelogram. And then one thing that we're going to use a lot, we haven't seen yet why this is important, but one thing we're going to do is we have to recognize if we know the directions of two vectors that we're adding together, but we don't know the magnitudes, what are all the possible directions that the resultant could be? So what if you know the directions of the vectors, the added vectors, but not the magnitudes? And the question is, what can you say about the direction of the sum of those two vectors? Okay, so let's say that we're adding a vector in this direction to a vector in this direction, but we don't know the magnitude. So the one in this direction could be this, or it could be this, or it could be this, or it could be even littler than that. It could basically have no length. They just all have to have the same direction. And same with this one. It could be really long, somewhere in between, tiny. Okay. So what can we say about the sum of those vectors? Well, if we added a really long one on the left to a really short one on the right, so there's the long one, and now we add on this tiny little one from the right, you can see that what we get back is the same vector. I have it drawn with that short one having a little bit of length, but it could be as small as you can think of, And so what you would get back is just a vector in the direction of the one from the left. And then you could do it the other way too. You could have a really long one like the vector on the right and add to that a tiny little one like the one on the left. And so what you get back is just the vector on the right. Okay. And those are the two extreme cases. But now what would happen if you made the long one a little shorter and the short one a little longer, what you could get is all of the directions in between those two. Okay. So to find the possible directions of the sum of vectors with unknown magnitudes, put the two vectors tail to tail, and then every direction between those two is possible. Okay. There's a pitfall here that you have to watch out for, and that is that when you're adding vectors, notice in my, let's see. Let me move this over here. Okay, notice when you're adding vectors, you have to go head to tail for the two vectors that you're adding, okay? Because the second leg of the journey starts where the first leg ended, okay? So it's head to tail. But in this case, where you're trying to represent all the possible directions from adding these two vectors, you have to put the tails together because it's a different thing. We're talking about all the directions in between these two vectors. Okay, so be sure you don't get confused about those. Okay, so that's vector addition. What do we know about vector multiplication? So multiplying a vector by a number or by a scalar. A scalar is just a word for a number as opposed to a vector. And we're going to think of this in two steps so that we can do positive or negative numbers that we're multiplying these vectors by. First, we're going to think of multiplying a vector by a positive number. And what that means is you keep the direction of the vector the same, and multiply the magnitude of the vector, the length of the vector, by that positive number. Okay, so for example, if you're multiplying 2 times this vector like this, you keep the direction the same, but the length is 2 times as much. So I'm going to put 2 of these here. And then the answer is just that. Okay, so it's twice as long, same direction. Now, how do you deal with negative numbers? Well, that's the second step of this, is multiplying a vector by a -1. And to multiply a vector by -1, you keep the magnitude the same, the length of the vector stays the same, and you just make the vector the exact opposite direction. You can think of it as switching which end is the head and which end is the tail. So -1 times a vector like this is in the same direction. Well, it's the same magnitude and it's parallel to this one, but we switch where the head is and where the tail is. Okay. And now with a combination of those two things, you can multiply by any negative number. Now you can combine vector addition and vector multiplication. So let's say that this vector A is like this, and the vector B is like this. What's 2A minus B? How would we calculate that? Well, 2A is going to be 2 times as long as A in the same direction. Okay, so 2A is going to be like that. And then minus B is going to be the same length as B and in the opposite direction. So since B is straight up, negative B is going to be straight down. And so the resultant, the answer, goes from the start of the overall path to the end of the overall path. Okay. And one thing that this is useful for is, remember, go back to the thing that we talked about where I said you could figure out something about adding two vectors with unknown magnitudes but known directions. You can't figure out everything, but you can figure out a range of possible directions for the sum. Well, notice that if you have, so let's say that you have a number times a vector u plus a number times a vector b. But let's say a and b are unknown, okay? Okay. Well, notice that that's the same thing as adding two vectors in the direction of u and v without knowing their magnitudes, because that, if you multiply, well, actually, this is something important about this. Let's say that those are unknown positives, okay? So if A and B are unknown positives, what that does is say that A times U can be any length of vector in the direction of U, and B times V can be any length of vector in the direction of V, okay? And so it ends up working out just the same as adding two vectors with known directions but unknown magnitudes, like the thing we already did. Okay, so for example, let's say that U is this way and V is this way. And even though we even though we know the magnitudes of those, because I drew some certain length for those, the fact that we aren't going to know what they're multiplied by is going to mean that all that matters is the direction. So what do we know about A times U plus B times V, where A and B are unknown? Well, that means we're going to be adding a vector in the direction of U, but unknown direction, to a vector in the direction of V, but an unknown direction. And so we just end up with a range of possible directions, everything from the direction of U to the direction of V. So again, put those tail to tail, and it can be any of those directions. One more thing that you're going to have to do is, what if A or B are negative numbers? How does that affect this? Well, a negative number switches the direction to the opposite. It effectively switches where the head is and where the tail is on the vector. And so if, let's say that A is a negative number, then A times U would be in the opposite direction of U, but could be any length. And so if A was negative, but an unknown magnitude, and B was positive, but an unknown magnitude, you'd have everything from a vector in the opposite direction of U to the same direction of V, and everything in between those two. So this is if A is negative and B is positive. Okay, so I don't think this lab activity is going to take a very long time. Please email and we can talk over Zoom or over email if you have any questions about this. And that's all there is to it.